Wednesday. The agenda today is to design a transmission shaft now with 3D mold circle. Okay, so this lecture will take, today I'm going to lecture for 1 hour 50 minutes. Okay, and the entire course to design transmission shaft will take about 3 hours, including example. Okay, so only mechanical engineers design transmission shaft. Okay, we do it intensively. We are so-called the specialists of designing of transmission shaft. This is because of we are mechanical. Mechanical, we don't do things as static. We tend to design structure that are both static and dynamic, i.e. that's moving. Okay, well, civil engineer will handle more of the static stuff. We could do it as good as them, but anything that is under dynamic motion is always mechanical engineers or material science, okay, but more mechanical engineers. So last lecture, we look at a transmission shaft, okay. So a transmission shaft over here, the formula that we're going to apply or we're going to derive with 3D mold circle is usually under two axes of so-called bending forces in the y direction and the z direction. So this Py and Pz will induce moment about the y-axis and the z-axis. Okay, and usually it's associated with a torque because this shaft will be rotating. Okay, so now one thing I want to elaborate is there is no axial loading, okay, for our transmission shaft. If that's axial loading, then the formula will not work. What we're going to derive will not work anymore. Okay, so we locate an element H over here. Okay, we found element, or we pick an element. So this element H, for now we pick a arbitrary location. Later on, based on the loading, we have to determine exactly at what location this element H has to be. Okay, so now when we look at element H, right, when we look at element H with the associated normal stress and shear stress, we realize that we have a normal stress in the x direction and we have a shearing stress in the xy direction. So from here, our stress state is stress x. We have negative stress. Now I'm just assuming it to be compressive. Okay, I'm not saying that it has to be compressive. I'm just assuming it's under compression. Then stress x and normal stress y and z directions equal to 0. The shear in xy, shear in yz is not equal to 0, but the rest of the shear stresses are all in 0. So i.e. what you see down here is we only have one magnitude of normal stress and one magnitude of shearing stress. Okay, the rest are all equal to 0. Now, let's look at the formula that we are going to apply to calculate normal stress in the x direction. Okay, so this is usually, I'm going to write out the overall general formula that you usually see. So what you will see is Px over A, right, plus by My over Iyy multiplied by Z minus by Mz over Izz multiplied by Y. So this is the general formula that we usually see. And for our case, okay, this will be equal to 0. Okay, why? This is because no axial loading. So the only two formulas that we need to apply is moment about y-axis and moment of z-axis to determine our normal stress in the x direction. Okay, so I'm going to highlight. So this is one very important formula that we're going to use in our design of transmission shaft. And what we realize over here, if we look at the distribution, okay, so I'm just going to sketch the distribution. So now this is our X. Sorry, this is our normal stress X. Okay, normal stress in the X direction. Then over here, it can be either our X distance or Y distance. Right, can be our one. So before I go on, I forgot to tell you there's no quiz for this week. Okay, your last two quiz will be on week 12 and week 13. Okay, so there's no quiz for this week. So if you look at the distribution in terms of Y and Z direction, okay, what we tend to have is we tend to have this sort of distribution. Okay, again, this is a sketch. Okay, so where we have compression on one side, okay, and then on the other side we have tensile. So this is our distribution. What we realize with our distribution is the maximum normal stress or stresses in terms of your stress X occurs when distance Y and Z are furthest away from the central. Okay, so i.e. at the radius, at the maximum radius. Okay, we know that. Okay, so that's for our normal stress. So if we look at our shearing stress, I'm going to write out the general formula for shearing stress. Okay, so the shear stress, you realize I did not write any direction over here, is equal to, before I go on, we know that, just to remind you, that this is under axial loading or axial force. Okay. This is due to bending moment. Now, in terms of shear, there's two shear components over here, or the general shear formula that we tend to see. So the first one is Tx multiplied by the radius divided by J, right? And then we have plus or minus the shear force By over Izz Qz over T. I put plus or minus is all depending on the direction of the shear force, okay? But it's not critical over here, and I'll show you why. And the shear force in Bz over Iyy Qy over T. And I'll put down here note that By is induced by Py and Vz is induced by Pz. Okay, so you get both your Py and Pz. Okay, let me put this somewhere lower, okay, because I have things to write. And in terms of shaft design, Okay, in terms of stuff design, stresses or shearing stress induced by the shear force are relatively small when compared to those induced by the torque. Okay. Okay. So they are relatively small when induced by the torque. So this term over here, right, is we assume it to be very small, and we assume it to be approximately equal to 0. Okay. So this terms over here are dropped. Okay. So we drop the shear force. Okay. So the only component that induce the shear is due to the torque. Okay. Is due to the torque. Now, this is, I'd like to elaborate, this is just a general formula that we make this assumption, okay? If you were to do this in industry, okay, you have to check, okay? So I'm writing you a set of formula where the shear force is very small. Sorry, the stresses induced by the shear force is small, and the shear stress induced by the torque is very large. Okay. Why I'm writing this so that when you apply this formula, you know the exact boundary condition. I think that's most important. Okay. So if we look at the shear stress distribution down here now. Okay. So now I'm going to draw the shear stress distribution. Okay. So this is our radius, and this is our shear stress. And what we tend to get is we tend to get a distribution looking like this. Okay, and a similar trend has been observed. Let me. Good. A similar trend is observed, okay, when it's torque induced. So this is basically is the torque, the shear stress, and it's induced by Txr over J. Okay. So what we see over here, again, the maximum shear stress occurs when the radius is the largest. Okay. So this is good news. Okay, this is because the stresses due to the normal stress is largest is also at the maximum distance from the centroid. So is the shearing stress. Okay. So now that is those are the formula that are required to find the normal stress and the shearing stress. Now we have to relate. Okay, now so we have to now relate